So while working with this solid state music I/O and parallel port card, I actually discovered an issue with the 1702 EEPROM card that we've put together. And let me show you what that is. So I've got a little basic program running here, and all it's doing is outporting and importing to the ports the two UARTs here on the board are on, just as a test. But what I noticed, and I'll have to pick the camera up here to show you this, is, oh, sorry about dropping that. With the machine running, you can see activity on the three LEDs back here that we added to the EEPROM board. And I was never happy with these EEPROMs in the previous video, or these LEDs. They just weren't doing what I intended them to do. And that created a bunch of confusion. And what I've realized here is that the ROM board itself is basically being activated during port I/O as well. And with the LEDs blinking the way they are, I suspect it's actually putting wait states onto the bus. And that's certainly not a behavior that we want. So to remedy this, I've looked at a couple of different schematics of yet other cards and realized I made a really fundamental mistake in the design of that ROM card. So let's jump in and look at that next. So now that we've discussed a bit the issue with the board coming active when it shouldn't be, I want to talk about the schematic changes I made to approach that. This is pretty much the original schematic with the addition over here where I was inverting A11 to move the address space of the card down 2 KB, as we talked about in a previous video. This was pretty much the schematic as the board was in that testing mode where I discovered the issue. Of course, we've got our address block decoder up here, A15 to A11, are decoded if in this case without using the inverter, so ignore this. We're connected directly A11 to pin 1. With those 5 pins 1, we get a 0 out takes these 3 pins and a 3 to 8 demux. And with the 0 here, pin 0 to 7 will come low, enable one of the 8 1702s. That goes ahead and then is ORed with SMR is high when the device is actually doing a memory read. That gets inverted low. We have a low coming out here, a low into the OR gate. That gates the data from the EEPROM onto the data input on the S100 bus. And this is a tri-state buffer and enables that buffer, and that generates then the wait states out on the machine to do the read. And the problem here was, again, just what's said again, is during port I/O, the card was coming active when it shouldn't be. And that has to do with the fact that on the 8080, we've discussed this before, there's 256 ports from 0 to 255 decimal. And the port address is put out on A0 to A7. That port address is duplicated on A8 to A15. And because that port address is duplicated on A8 to A15, these address pins come into play. And this was just getting accidentally enabled when it shouldn't have been. It didn't seem to affect operation of the machine, but it really bothered me because it was just incorrect. So the changes that were made to the schematic are as follows. This circuit down here that dealt with SMR, that memory read signal, has been removed. SMR and PD bin have been moved up as inputs onto the 8 input NAND gate. These both go high. So this goes high when we want to read memory, and this goes high saying the data should be on the input bus. So if the machine, in this case, I've got these two connections jumpered. So A11 is coming in directly to pin 1. With A11 high, A12 to A15 high, and both of these high, it's saying, hey board, I want you to actually read some data from the ROM. This output enabling in goes low. The 3 to 8 demux happens. 1 of 8 ROMs is enabled. That low enables these tri-state buffers, so the EEPROM data is presented onto the S100 bus on the DI pins, and it enables this tri-state buffer, which passes the wait signal on through to delay the board so the EEPROMs have enough time to actually get data out valid. This had the effect of completely surplusing that 7432 device D. All 4 gates here are now in the extra list. There's 4 leftover inverters. We've got the one inverter here we're using to be able to invert A11 I invert A11 simply for testing. By inverting A11, we move the board down 2K in the address space of the machine. And by doing that and then enabling the original Altmon up in the upper 2K of space, I can then use a little basic program to compare the bytes I've programmed into the 1702s to the bytes it's reading out of the actual ROM that's up in the normal 2K space. We used this in a previous video to basically detect programming errors. I added 3 LEDs. Really, only 2 of these are now used, or one of these is actually only used, and that is the enable LED lights up when the board's actually active. Remember, output enable goes low. This is what it is because device I down here. See, pin 15 on device I is those 2 guys. Because I needed to enable this, so this tri-state buffer and these 3 are ganged together with pin 1 being the enable. And because I wanted output enable going low to gate that delay signal onto the bus, it also has the effect of turning these 3 devices on or off. And so when it goes low, these tri-state drivers become active. The 0 that's on here gets passed through. That's why that kind of looks kludgy like that, is the fact that it's a shared pin here. Get in the 4 ganged tri-state buffers. This LED comes on when the board's being accessed. These 2 aren't doing anything at the moment. Really probably won't do anything. It is what it is. They're on the board. They're soldered in. I'm not going to remove them. But these are the changes I made to get the board at least working to my satisfaction. So the first thing we need to do here is remove some of the wiring I already have on the board. So I'm going to disconnect 2 of these LEDs just because at the moment they're not needed. I think that's a good first start. So I want to get to device I, get the other glasses on. Device I, pin 6, and I'm going to lift that input. So 1, 2, 3, 4, 5, 6. And I'm actually using a wrap tool here that's designed to unwrap. And that's coming from, I'll quit dragging the paper around. That would be coming from pin 3 over here on device D, which it is. So let me try to unwrap that one without disturbing the wrap below it, even though it's going to come off. And then I want to go to pin 10 on device I. Device I, pin 10, and that goes to pin 9 there, so that lead can come off. That's just a single wrap on that pin, and that's going to pin 9 up here, so we can remove that wrap. And hopefully that'll just leave those LEDs not activated. They're just sitting there with the really with the drive leads, and we'll leave that the way it is for now. I want to get to pin 47 on the bus. '49, '48, '47. I wish that fold in the paper would quit catching on the pins on the front of the board. And that's where I'm picking up SM read. And I'm just going to completely remove that lead. And that should be running to pin 1 on device E. And it is, which is this wire right here. longer need to be inverting that signal. See if I can pluck that wire up out of here because it's now buried under a rat's nest. See if I can pull it through and out. And then pin 2 of device E, which is where I'm at, goes to pin 2 of device D, which it does. That gets completely floated out. Pin 3 of device D let's see how easy that's going to be to remove. Pin 3 of device D. Okay, on pin 1 of device D we have 2 connections. Let me pluck out pin 3, device D. And that's coming to pin 15 and 1 here. Where's that lead go? There are multiple wraps on there. There are. But that's okay. I just need the upper wrap removed. And that leaves pin 15. Doggone it. Pin 15 and 1 should be connected, and they should go to 15 of device I. Let me get a mirror here just to make sure that is what I'm seeing. So pin 15 and 1 of device H should be connected. Did I just pull that off the wrong? Ah, that's where it come to. Okay. So on device I, pin 15, I should connect to pin 15 and pin 1. So this is still wired together, we've just isolated it. So that is gone. We still have 7432 pin 1, which goes to 2 places, looks like at the moment. Which is a mystery why that goes to 2 places. Device A. That doesn't make any sense. Device D. What have I done here? So device E, pin 2 should be floating, and it is. Device E, pin 1 is floating, and it is, so we've isolated that. Device D has got 2 leads coming off of pin 3, or no, pin 1. Okay, one of them goes to device I. Okay. It's going to device I, pin 1. Which doesn't make a lot of yeah, we need to pull that off as well. Okay, I see what I did. And then it goes to device I, pin 4. Device D, pin 1, is also going to device A. I got 2 more leads to unhook here. Because of the order of the wire wraps, this is a little more difficult than I wanted it to be. And that's going to pin 1 over here. And that leaves that gate completely isolated. So now we need to start adding wrap wire. We've got device I, pin 8, which is going to go to pin 4, pin 1, pin 1 there. Actually, let's pull the schematic out here for what we did. And look at wiring this. Where's the yellow wrap wire? So we should have, and that printout's a little fuzzy. We got pin 8 of device A. Pin 8 of device A going to pin 12 of device B. And it does. I also need that to go to pin 1 of device I. Pin 15 So we confirmed those pins are connected down there. So we're going to take, trying to keep the number of wraps on a post to 2 max. So we're going to take pin 12 here. Which already has 1 wrap to it. So we'll add a second one. We're going to take that to pin 1 of device I. Hopefully I'm somewhat on camera here. Pin 1 of device I. And that also needs to go to pin 1 and 15 and 15 of device I. So that really just needs to jumper to there, and that should hook that entire block up. So device I, pin 1. Over to pin 15, device I, assuming I can get the wrap wire in the tool. And what that should give me, so device B, pin 12, should be connected to device A, pin 8, should go to device I, pin 1, should go to device H, pin 1 and 15, and should end up on, see, that's already I, pin 1 and I, pin 15. So I think we've got that all hooked together. So the last, do we need to do anything else here? That's really kind of interesting. I pin 1's really covered here twice. Let me get the original schematic back in here and look at this. So we know we got output enable hooked to there. We've got it going, we know, to these pins here, that pin there, and that thing. All we need to do now is bring in SMEM read to pin, well, one of the pins here on device A. And I've got pins 6, 11, and 12. All hooked together. Isolate 6. Now I need to isolate it. Oh, come on. Now isolate 6, that's what I've drawn here. In this case, I'm just going to cut the wrap wire off. Just because the order these are stacked, it would be difficult. I'd have to completely remove all those and put them back on. So I really am just going to cut off this lead. And we're going to take pin 6 now, which has got a control signal on it, SMM read. Pin 6 of device A to pin 47 on the S100 bus. And SMM read goes high when the system wants to do a memory read. So that's a much simplified, and should only enable this board when we're doing only memory reads. From the address space that we're interested in, as we talked about a little bit earlier in the video. So 49, 48, 47. 47 is SMM read. It's going to pin 6 of this device. That really, I believe, should be all we need to do here. That wasn't too bad to reconfigure. We can look at this from the front of the board as well. So 49, 48, 47 should be going to pin 6. Device A, pin 8. Need the other glasses. Pin 8 should be going to line B that way. Oh, come on, leads. Why do they have to tangle up like that? Pin 8 should be going to pin 12 of device B. 8, 9, 10, 11, 12. It should be going to pin 1 of device I. To pin 15 of device I. To pin 1 and 15 of H. See, 8, 9, 10, 11, 12, 15, counting wrong. So we've seen it connect to there, seen it connect to there, there and there, there, and there. That should be it. That should be all the changes we need to hopefully get this board to operate a little bit better. These stickers should no longer be relevant. I think that's going to do it. So the next step is to go put this back in service and see if it works. So apologies for the handheld video here. It's kind of where I am. So we've made the modifications to the card as discussed in that final schematic we looked at. And I'm going to go ahead now and apply power to the machine. And it's just hard to do with one hand. I'm going to reset the machine. I'm going to examine address FF00, and we should see that LED marked board enabled light up, and it does. So that's a good sign. So that says we're reading the board. And if we look up here at the status LEDs, we can see we're reading the first byte off that board. So if we now go in, let me power up the floppy drive. And I run at this address, you should see the board enabled LED blink and then go out as the machine boots. And that was really quick. But it's exactly what it should have done. It read enough of the boot contents out of that FF00 ROM to get the machine booted up and running BASIC, and now the card's no longer being accessed. So let me now go in and I'll load up the BASIC program that was testing that SSM serial I/O card, and we'll see if the LED issue comes back. So I've got the BASIC program running that is exercising the UART. It's writing out of one and reading from the other. And you can see here that I've got the two UARTs, 2 to 3 and 3 to 2 swaps, so that basically one UART writes to the other, and then the other one writes back to the other one, so they're just kind of writing in a circular fashion. And during all this I/O activity, the card's no longer being accessed. This is, it should be, that board status LED, the board enabled LED is off. So this fix has worked, as discussed in the schematic. So it's progress, and now I can get back to all the other projects going on the machine. So anyhow, I'll wrap this short bit of video here up, and we'll talk soon.